Good morning, everyone, and my name is Ayush. My student ID is st20333333. Today, I'm presenting my presentation about algorithm design analysis, which is regarding how the implements work. So, I'm presenting on optimizing smart navigation using the a pathfinding algorithm for a module CMP 7002 algorithm design and analysis. Over the next 10 minutes, I will take to our algorithm designs and have gold standard for the intelligent navigation systems from autonomous vehicle to robotics and smart city applications. Let's go to introductions. In introduction, we can see the overview of pathfinding and the modern navigation systems. Pathfinding, let's begin with some context. Pathfinding isn't just an academic exercise, it's a creating technology that powers many systems we interact with daily, from the GPS, like in the phone, to autonomous vehicles. Navigations we are already using in our daily needs, which we are using like a GPS, and from robotics in warehouse to a game AI. Just the challenge is the system faces finding routes that they are just short but also safe, efficient, and reliable, so people can save money and time. Environment abstracts at complexity. Think about decision making, road closure, changing weather conditions, or time problems. This is where sophisticated algorithm design may become crucial. Then algorithm we've explored today representing an elegant solutions that balance computationally efficiency with optimal math finding. Good algorithm designs here directly translates to better performance, good improved reliability, and the ability to scale these problems to systems to larger, more complex environment so that we can use it very fluently. In the third slides, I'm showing more problems, statement justification, how it pairs and how the solutions, the justification, how it we gonna justify. So the what's the main problem, core problem we are addressing in motor applications, particularly robotics, autonomous vehicles, digital mapping systems, and the keyword is real time. The real systems can afford to spend several calculating a route which while a car is moving at a highway speeds or a robot is navigating a dynamic dynamic warehouse. Solution for we develop need to three things: optimal meaning they find a best path, complete meaning they find a path if one exists, functionally economical so they don't consume excess power processing memory. Traditional algorithm often struggles in large or dynamic environment. For example, Dijkstra algorithm will find the optimal math as we seen on the video in the problems. Uncertain node, but it explores too many uncertain nodes. Greedy algorithm is fast but don't guarantee its optimal solution for the to the area and the era today we are using. This brings us to a algorithm strikes an elegant balance by combining the actual cost of reaching a node, the g value with the estimate node, so that we can gonna be a optimal and efficient, particularly in grid based and switch to driven navigation, which are exactly the environment we can see in the model applications. Next my fourth slide is a literature view in which we can just look what research tell us about pathfinding programs, algorithms. A algorithm was introduced by Hart, Nilsson, and Raffer back in 1968 and stood the test of time as an optimal graph search algorithm. The key to its success is the use of admissive heuristics, heuristics that never overestimate the cost to reach the goal. This ensures we get optimal solutions. We can see in the diagram that's the inputs how we can tackle the nodes. The algorithm uses simple but powerful cost function fn equals we can see gn plus hn plus gn representing the cost from the start node, and hn is a heuristic estimate from end to the goal. Now let's compare A to the common algorithm. Looking at this table, we can see trade-off clearly. Dijkstra algorithm always find the optimal path, but is slow. but it doesn't use any guidance. Greedy best first search is fast because it considers the heuristics, but this means it's not granted to find the optimal path. In A combines the strength. It's both optimal and fast, so this comes at a higher cost of higher user memory. More recent videos like jump point, search, and delight offer even fast performance for specific scenarios, so they are more complex to implement. Looking at current search gap, the state-of-the-art navigations need versatile heuristics to handle varying environment, real-time applications, increasing more efficient of A due to strict performance requirement, and there are plenty of theoretical research. There are many gaps in practical and future studies for real-world smart education systems. So this is literature view. I will talk about this as a strength and greedy first, and JPS algorithm of faster JPS delight. Now this is a gap. We can saw that gap in the literature how that is working. This is a gap which varies most of the important in this presentations. In process of which what we are proposing, our system objective is to develop an A-based smart navigation system so that can efficiently compute the shortest path in a grid-based environment. The architecture is straightforward but effective. The key components are first we take input in the form of map or grid representing the environment. This feeds into a path algorithm engine. This processes the data and compute the optimal path. The output is the route where we can visualize or fed into navigation systems. So last one is optical extractions. Optical extractions we can enhance the individual GPS-based systems. We can see on the PPT. This and jump points is saturation for better and performance in large grid. Next one is proposed solutions. So in which we can system flows a clear pipeline. Input leads to pre-processing, which way we validate map, prepare data structure, then a validation engine takes over the computation, which produce the path comparison results, and finally we output the route in a stable flow of flow chart of a algorithm. In this first we can analyze the opening and the close list. We can install two lists. The open list which contains new nodes we need to explore, starting our start node and a close list which track nodes we have already evaluated. The algorithm then enters into main loops. We select a node from the open list with the lowest fn value. Remember that g plus h, the sum of actual cost and our estimated cost. This is the most compromised node to explore next. Next we expand the neighbors nodes of our current nodes. For example, each neighbor will calculate or update three keys value g, the actual cost to reach that neighbor, h, the heuristic estimate from the neighbor to the goal, and f their sum. Then it comes a critical check. This is a current node, our goal. If we yes we are done, we reconstruct and return the path. So if not, we do not move the current node to the closed list and continue the process. The algorithm continues this loop until either we find a goal and open list become empty, which would mean to no path exist. This system exploration guided by heuristics, which makes is so efficient compared to undefined such algorithms. Next slide is computational complexity analysis. Let's analyze the computing performance of A, which directly address learning functions outcome. 5 regarding quantitative analysis of algorithm performance, starting with the time complexity. In a typical scenario with efficient data structure like priority queries, I could perform at O, EV log V, where E is the number of edges, V is the number of vertices. This is quite efficient for most practical application. However, the worst case scenario is O, B to the power of D, where B is a branching factor, how many neighbors each node has. D is a tough solution. The worst case occurs when a use is weak or misleading, essentially may behave more like a uniform search. For space complexity, where A faces its main limitations. The algorithm require significant memory to store both the open list containing frontier nodes and closed list tracking visitor nodes. In large environment, A can actually be limited by RAM rather than processing power. This analysis highlights a fundamental trade-off in algorithm designs: achieve complementarity and good overkill performance. This comes at a significant cost in memory usage. Understanding this trade-off is essential when deciding A is appropriate for our given application so that they can work. Last slide is overall the results which we have proper given from the last slides. Results, we have outcomes that we can expect for implementing the system. First and foremost, the algorithm will produce optimal and efficient path, and optimality is granted by a dimension of heuristics, which by efficiency comes from the heuristic guidance. Through heuristic turning, we can achieve a more route termination for a specific time environment. For example, using Manhattan distance in grid-based setting or increased resistance when the diagonal movement is allowed. Compared to a conventional algorithm like Dijkstra and PFS, we expect clear performance improvement like in terms of nodes, export and communication time, so that find this works identify clear as areas for future enhancement, including real-time interactive updates for navigations, scenarios, and more sophisticated and user designed for complex multi-objective orientations. Last one, conclusion. So we can have a conclusion like a summary from all the slides. This is the main motive to conclude a algorithm represent a fast and efficient solution for smart navigation challenges. It constantly highlighted in the literature and the optimal approach, effective balance and communication efficiency with the path optimally compared to traditional algorithm. So that we can I already highlighted points over there. So our proposed system takes these established benefits and packages them into practical navigation model that can deploy it in real scenarios. Looking ahead, next one topic is looking ahead. The next steps for research include full implementation testing with the real world data assets, comprehensive performance evaluation, data across different type of environment types, enhancements to GPS and D-Lite variant for better performance, and ultimately developing for real-time dynamic navigation where the environment changes during the path computations. And last next steps is last one, air algorithm despite being over 50 years old remains at the heart of modern navigation systems, ongoing optimization and recommendations and variants. It will continue to power the intelligent system tomorrow. Thank you for the attention, and I'm happy to take any questions. So this is a reference I taken from the books where you can click from a PPT. This is a links with the books. This is the main things took many references, so we can took from the internet. That's it. Thank you from my side. Hopefully you are good, sir. Thank you.